Hai, Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Nazhan bin Abdul MALEK and I'm representing Group 10. Today, I will be presenting the first part of our group project for the course CSF20203 Algorithm Design and Analysis. Our project is titled Class Timetable Scheduling. In this presentation, we will explore one of the most important yet complicated tasks that universities handles every semester, which is the creation of a class timetable that is efficient, fair, and free from conflicts. We will be analyzing different algorithms and evaluating which one is the most suitable for solving this problem in a real university setting. Together with my group members, FAWWAZ bin KAMARUL SHUKRI and RIDHWAN bin YUSOF, we have divided the task and collaborated to explore this problem from different algorithmic perspectives. Now, I will begin by explaining the case study and the core problem we are trying to solve. Now, I will explain about case study and problem recap. So the case study we selected is called Class Timetable Scheduling. This is a real-world issue that every university faces, on how to assign hundreds of classes to a limited number of time slots and classrooms while ensuring that there are no conflicts. To do this, we must consider two categories of constraints. First, we have hard constraints. And then second, we have soft constraints. So for hard constraints, these are the rules that must never be broken. For example, for hard constraints, which is a lecturer cannot teach two classes at the same time, a room cannot be used by two classes at once, the number of students in a class must not exceed the room capacity. And for second, we have soft constraints, which are more like preferences. These include things such as avoiding early morning or late afternoon classes, giving breaks between classes, keeping classes on the same day or in a specific block of time. So the main objective of our project is to build a timetable that respects all the hard constraints while trying to satisfy as many soft constraints as possible. This is not just a technical challenge, it's something that affects the daily lives of lecturers, students, and administrative staff. A good timetable improves learning efficiency, reduces stress, and helps the university use its resources properly. On the other hand, a bad timetable can lead to missed classes, lecture overload, and poor use of rooms. That's why solving this problem using algorithmic techniques is so important. We move to the next slide. So now, I will explain about the chosen algorithms and summary of key findings. To approach this scheduling problem, our group selected 3 algorithms for detailed analysis, which is RIDHWAN algorithm, backtracking algorithm, and genetic algorithm. Each of these algorithms represents a different strategy for solving problems. Let me briefly explain what we found when analyzing them. First, the greedy algorithm is a simple and fast method. It makes decisions one at a time, choosing the first available time slot and room that meets the basic constraints. This approach is useful when speed is the main goal, and it works well when there are not many conflicts. However, one major weakness is that once it makes a decision, it does not go back and change it, even if a better option becomes available later. That can lead to problems in more complicated schedules. And second, the backtracking algorithm. This one is much more thorough. It tries all possible combinations of time slots and rooms. If it finds a conflict, it backtracks and tries a different combination. It's very accurate and guarantee a valid result, but it takes a lot of time, especially when the number of courses increases. Because of that, it's not practical for large universities, but works well in a small scale, high accuracy scheduling tasks like exam timetables. And third, we have the genetic algorithm. This algorithm is inspired by natural evolution. It starts with random schedules and thorough generations of improvements using operations like selection, crossover, and mutation. It creates better and better timetables. What makes it strong is that it can handle both hard and soft constraints, and it works well even when the scheduling problem is large and complex. While it doesn't always find the perfect solution, it can find a very good one in a reasonable amount of time. So in summary, greedy is fast but limited, backtracking is accurate but slow, and genetic is flexible and scalable. Now I will explain why our group chose these three algorithms. So now I will explain to you about algorithm selection rationale. When we were deciding which algorithms to use, we wanted to make sure that we had a balanced selection, one that represents different problem-solving approaches in computer science. That's why we selected greedy, backtracking, and genetic. So greedy, which is a heuristic algorithm, it makes quick decisions without looking back. And for backtracking, which is an exhaustive search algorithm, which is, it checks all possible combinations and ensures correctness. And genetic, which is a methoristic, it uses randomness and adaptation to solve complex problems efficiently. Each one has its own strengths and weaknesses. By analyzing all three, we could make a proper comparison and understand which one works best for different university situations. We also considered other algorithms like brute force, simulated annealing, and constraint satisfaction programming. However, we decided not to include them because brute force was too slow and impressional, simulated annealing was similar to genetic but offered fewer advantages for our case, and constraint programming required advanced tools and would take too much time to implement. So in the end, we made our decision based on practicality, variety, and how well the algorithms match the complexity of real university scheduling problems. This decision was made autonomously within our group. We discussed, compared options, and voted fairly. Each group member contributed ideas and we made our final choice based on research and critical thinking. Now that we have explained our algorithm selection, I will move on to the decisions and assumptions we have made during our analysis. This section is important because it shows how we approached complexity evaluation in a realistic, practical way, not just from a textbook perspective, but by thinking about how the algorithms would work in an actual university setting. To begin with, we had to define the variables that would help us analyze the performance of each algorithm. These variables reflect the typical components involved in class scheduling. First, we assume N to be the number of courses that need to be scheduled. This is usually a large number in most universities. For example, in our case, we assume more than 500 courses in total. Next, T represents the number of time slots available per week. These are the available teaching periods across the university calendar. For example, if the university runs classes from Monday to Friday with 12 periods per day, that gives us 60 possible time slots. We also define R as the number of rooms available. In a big university, this could be around 50 or more, including lecture halls, tutorial rooms, and labs. For genetic algorithm, we had to introduce two additional variables. These are P, the population size, which refers to how many complete timetables are evaluated in each generation, and G, which is the number of generations the algorithms runs through. These variables are essential for estimating how long the algorithm will take and how much memory it will use. Now, beyond just defining the variables, we also considered the nature of the data. We modeled the data based on a large university environment, which means the scheduling problem involves hundreds of classes, dozens of rooms, and many overlapping students and lecture schedules. We assumed a realistic academic load, where solved conflicts like back-to-back classes, lunch breaks, and avoiding Friday evening classes are common. We intentionally made our model complex enough to test the algorithms under realistic pressure, not an ideal simplified version. An important part of our analysis involves breaking down the time complexity of each algorithm into three cases, which is best case, expected case, and worst case. This helps us understand how the algorithm might behave in different conditions. The best case scenario assumes everything goes smoothly. For example, course get scheduled without needing adjustment or backtracking. This is rare but useful for understanding the lower bound of performance. The expected case is more practical. It assumes more conflicts will occur and the algorithm will need to do some work to find valid assignments, but not to an extreme level. This reflects what will likely happen in a real semester. Finally, the worst case is when the algorithm struggles to find valid combinations due to high conflict or a shortage of resources. This helps us measure the algorithm's limitation. By using this realistic assumption and modeling techniques, we made sure our time and space complexity analysis wasn't just theoretical, but also connected to actual challenges faced by university administrators. These decisions gave us a solid foundation to compare the algorithms fairly and make an informed recommendation later on. Now, I'd like to give a deeper explanation of the trade-off between the three algorithms we analyzed. Understanding trade-offs is important because in most real-world problems, including timetable scheduling, there's no perfect solution. Instead, we have to choose the algorithm that offers the best balance depending on the situation. Let's begin with the greedy algorithm. Its biggest advantage is speed, because it doesn't look ahead or backtrack. It can generate a schedule very quickly. This makes it suitable when we need a timetable urgently or when the problem is relatively simple. For example, when there are plenty of available rooms and minimal conflicts. The greedy algorithm also uses very little memory, which is ideal for environments with limited computational power. However, the trade-off is that it's not very smart. Once it assigns a class to a slot, it doesn't check whether that decision causes problems later on. So, if it makes a poor decision early in the process, it can ruin the overall quality of the timetable. It also doesn't handle soft constraints well, meaning it may create schedules that are technically valid but frustrating for students or lecturers. So next is the backtracking algorithm. This one is the opposite in many ways. It's extremely accurate and it guarantees that the final timetable will satisfy all constraints if a solution exists. If it does this by checking every possible combinations of class placements and backing up when it finds a conflict. The benefit is obvious. We get a correct, conflict-free schedule. However, the cost is time. As the number of courses and constraints is increased, the algorithm has to do exponentially more work. This makes it impractical for full semester timetabling, especially at larger universities. But for the very critical schedules, such as exam timetables, where accuracy is more important than speed, backtracking is a good option. Finally, we have the genetic algorithm. This one tries to find a good enough solution rather than the perfect one. It uses the idea of evolution, generating a population of possible schedules, evaluating how good they are using a fitness function, and then improving them over time using crossover and mutation. The strength of this algorithm is its flexibility and scalability. It can handle both hard and soft constraints, and it works well when the scheduling problems is huge and messy. It also gives us control. We can adjust the fitness function to prioritize what the university cares about most, such as minimizing gaps between classes or avoiding Friday evening slots. But the trade-off here is that it requires more memory and it needs careful tuning. If we don't set the population size or number of generations correctly, it might not give good results. Also, it doesn't guarantee a perfect solution, but in most cases, it gets very close and close enough to be useful in real applications. To summarize the trade-offs, the greedy algorithm is fast but not flexible, and the backtracking algorithm is accurate but very slow, and the genetic algorithm is flexible and practical but requires more memory and fine-tuning. These trade-offs are important because they reflect real-world constraints. In a university, we usually don't have unlimited time or resources to compute the best timetable. So it's better to use an algorithm that can give us good quality schedule in a reasonable time, even if it's not perfect. This is why understanding trade-offs is just as important as understanding complexity. It helps us choose the right tool for the task depending on the situation.
Assalamualaikum warahmatullahi wabarakatuh. So for the group decision making process, the first one is role assignment. One member per algorithm for primary research. This means each group member focus on one algorithm and did deep research about it. One member for editing and formatting. This member check all the work, fix any mistakes, and make sure the format was the same. And for the one member for coordination and deadline tracking, this member make sure everyone follow the schedule and reminded the group of deadlines. Second is decision autonomy. We chose algorithm independently after brainstorming. After sharing ideas together, each person chose their own algorithm based on what they liked or understood best. We created evaluation criteria together, like speed, memory, scalability, constraint handling. We discussed and agreed on how we will compare the algorithms using these 4 points: speed, memory, usage, and ability to handle big problems, and handling special rules or limits. For the third is conflict resolution. Disagreements were settled by group voting. If we didn't agree on something, we solve it by voting, which is majority wins. Tasks were redistributed when needed to avoid delays. If someone was busy or had a problem, others helped or took over their tasks so the work wasn't late. And last is accountability. Progress updates shared on Google document every 3 days. Every 3 days, we updated our progress in a shared Google document so everyone could see what's done and what's left. Each member reviewed at least one other member's work. Everyone had to check someone else's work to make sure it was correct and clear. For the supporting evidence for final recommendation, why the genetic algorithm stands out. Balance of hard and soft constraints. Successfully handled real university constraints like lecture, overlaps, and student break preference soft using a weight fitness function. This means it could follow strict rules like no two classes at the same time, and also respect student preference using a scoring system. Scalability demonstrated effective even with 500 courses, 50 rooms, and 60 periods in simulation scenarios. It still worked well even when the problem became very big, which shows it's suitable for real university timetables. Adaptability to policy changes. Easy to adjust fitness weights to reflect institutional priorities, like no classes after 6 p.m. and free Fridays. We can easily change the settings to match what the university wants without restarting the whole process. Performance efficiency. Though not optimal in every case, results were consistently near optimal and completed within a reasonable time frame. Even if the result wasn't perfect, it was always close to the best and finished fast enough for real use. Consensus decision by the group. All group members evaluated trade-offs and reached a unified decision based on performance across all metrics. For this, everyone in our group agreed that genetic algorithm was the best overall after comparing all the important factors. So for the conclusion, what we learned: different algorithm types solve different problem scales. We found that some algorithms are better for small problems, and same work better for large and complex situations. Theoretical performance must always be evaluated against practical use cases. Just because an algorithm looks good in theory doesn't mean it will work well in real life, which means we must test it in real-world examples. Algorithm suitability: greedy, best for emergencies or small departments. It gives fast results and is useful when time is short or the system is not too complicated. Backtracking: best for high accuracy exam scheduling. It checks every option to avoid any clashes, so it's great when accuracy is very important, like in exam timetables. And genetic: best overall for scalable, multi-constraint semester planning. It can handle many rules at once and still give good results, even for big timetables with many classes and rooms. And the last is project reflection. This assignment showed how to apply academic algorithm knowledge to a real-world system. We learned how to use what we studied in class, like algorithm, which to solve a real problem, which made the learning more meaningful. That would be all. Thank you.